In the last video, I explained how you can build an Arduino-based command station even if you do not have a lot of experience with electronics. Today I'm trying to take this a step further and show how to use the DCC AUX LED chain to display turnout positions, block detector statuses and more. Welcome to the IoTT channel. I'm Hans Tanner. A special welcome to all new subscribers and welcome back to everyone else. I'm happy to see you back here. If you take a closer look at the DCC AUX Shield, you see an RGB LED and close by a row of 3 soldering pads labeled W, G and R. The LED is number 0 in a string of Neopixel LEDs and the soldering pads can be used to connect an entire chain of them. To use the Neopixel chain, an IoTT stick must be installed on the board. Neopixels are RGB LEDs which can be programmed individually to display a specific color and brightness. You can buy them in various forms, either as matrix or as strip or even single nodes, which I used, for example, to build the searchlight signals shown in video number 13. The DCC AUX board makes use of WS2812 type LEDs with an operating voltage of 5 volts. These WS2812 strings are connected with a 3-wire cable with 5 volts ground and the control signal. Therefore, the labeling of the soldering pads with signal names on one side and the typical wire colors white, green and red on the other side. Simply solder the wires of your LED string to the board. Best practice is to use a pigtail connector to make it pluggable. So, once connected, what can the LED chain be used for? Well, basically all kind of illuminations on the layout. Signals as shown in video number 13. A CTC panel as shown in video number 9. Commercial 3 LED signals as shown in video number 22 and more. What is really nice is that all LEDs are simply daisy chained using a 3-wire cable, which greatly simplifies the wiring and allows for inserting or adding new LEDs anytime. Here is how I want to use these LEDs in this video. I want to connect block detectors to some inputs of the Arduino board and show track occupancy on the LED matrix and in JMRI. I want to operate turnouts from engine driver or JMRI and have the turnout position displayed on the LED matrix. I also want to be able to trigger a list of turnouts, also called a route, with one command and have a special LED indicating if the route is set. To set the turnouts and trigger the route, I also want to be able to use local buttons connected to the Arduino inputs. Of course, when operated locally, the turnout position and route status should be updated on the LED display and in JMRI as well. Sounds complicated? Not really. I would say these are the everyday requirements for building a layout control system. What makes it challenging is that none of the systems I plan to use, so the Arduino command station, the LED display or the JMRI software, can do everything I want, and on the other hand, some functionalities are available on more than one of these tools. So we have to do some system integration, which means we have to decide what functionality of each subsystem we want to use and how we want them to communicate to meet the overall requirements. To gain an overview, it is a good idea to create a little matrix showing what requirements can be met with what system. Based on what I want to do, I can see these requirements. For occupancy detectors, we need to have functionality to define inputs, give them a number and then receive status information. The LED display needs to provide the functionality for defining what each LED should display, and then actually drive the LED in the desired color and brightness. For turnouts, we need to be able to define turnouts, match them to an output or DCC address, and operate them by sending position requests. For routes, we need to be able to define a list of turnouts and positions, and then execute the list with a single command. For local buttons, we need to be able to define inputs that can be used for triggering turnouts locally. And then IoTT. This stands for if this, then that, and means the functionality needed to trigger action based on events. This is an example. After clicking a local button, a turnout position request is sent to the right address and for the correct position. This is my initial list of requirements, and it is very well possible that it will get expanded as we go on. In the columns of the chart, I list the available systems I want to somehow integrate. I begin with JMRI or any other PC-based software to be used to send commands and report input statuses. Another possibility is Engine Driver or another smartphone app with limited functionality compared to a PC-based solution like JMRI, but capable to issue some commands. Then the IoTT Stick connected to either a DCC AUX or a Red Hat Shield. It is used for communication to DCC-X and for driving the LED matrix. DCC-X is the DCC signal generator and has a number of additional input and output pins. And finally, X-Rail is a subsystem within DCC-X. I list it here as a separate system as it is not available in the out-of-the-box DCC-X setup. If we want to use it, we need to do some additional programming. Now we can populate the matrix with the capabilities of each system. Most of it is straightforward and needs no further explanation. One area that is worth to have a closer look is the functionality of DCC-X as out of the box, compared with what can be added when using X-Rail. Out of the box, DCC-X is basically just a DCC signal generator and input status collector. That means it can be used to send DCC commands for locomotives and turnouts to the track. In addition, it can be used to define and operate Arduino pins in output mode from turnout commands. And it can define Arduino input pins as inputs and report the status every time there is a change, and it is also possible to read out all defined sensors and turnouts along with the status or current position. But what it cannot do is defining routes and any kind of IoTT functionality, so it is not possible to operate the turnout as a result of a change of an input. This would require the X-Rail module activated, which in turn requires the user to make changes to the DCC-X source code and redeploy it to the Arduino board. That is not really hard to do, but remains a mystery for many users, and therefore is an additional hurdle to overcome. So for this example, I decided to show both possibilities, implementing the functionality without X-Rail in this video, and then looking into using X-Rail to basically do the same but different in the next video. So here is what we need to do to implement our example using an Arduino command station with an out-of-the-box DCC-X system. First, we define the inputs for sensors and local buttons. Then we define the turnouts. Next, we define the LEDs we want to use to display status information. And finally, we set up IoTT for using local buttons to operate the turnouts and trigger the route. Let's do it step by step and start with setting up the sensors and buttons. Here is a table of what pins and addresses I want to use. For the track occupancy sensors, I plan on using Arduino inputs 23, 25, 27 and 29, and they should be converted into Loconet input messages from 101 to 104. The logic is set to negative so that the low input voltage on the pin means that the track is occupied. Then I use the input pins 47, 49, 51 and 53 as button inputs to set the turnouts and trigger the route. Button 47 will be used to toggle turnout number 1. Buttons 49 and 51 will be used to set turnout 2 to closed or thrown, and button 53 is used to trigger a route which sets both turnouts to closed. Once I have defined all pins, I can enter them using the Red Hat tab of the IoTT Stick. Click on the Inputs tab, create the number of required entries, and enter the information from the table. To store the information, there are two options. I can store it locally on the IoTT Stick, and it will be downloaded to the Arduino every time the IoTT Stick starts up. Or I can check the EEPROM checkbox and have the settings stored on the Arduino permanently. The advantage of storing on the IoTT Stick only is that there cannot be any conflicting settings, while the advantage of the EEPROM method is that the settings remain permanent in case the Arduino gets restarted. There is a third method, actually my preferred one, and that is defining sensors and turnouts in X-Rail, but that is something to cover in the next video. We can now test the settings so far by opening the Loconet viewer and pull the pins to ground. Each time a pin is pulled or released, we should see either an input report or a button message. Next, we define the turnouts. Again, I start with a little table to define what I want to do. In this case, I want to set up turnouts 1 and 2. Turnout 1 thereby is a DCC turnout, which means the Arduino shall send a DCC turnout command via drag to an accessory decoder. Turnout 2 is a pin turnout for pin 22, so the Arduino pin will toggle between ground and 5 volts depending on the turnout position. To set it up, I click on the Turnout tab and create two entries with the settings as defined. The ID will default automatically to the next available unique value, but you can override it as long as you make sure the value is not already in use, either as Turnout ID or Sensor ID. For the DCC turnout, you can set the pin number to 0 as it is not used, and for the pin turnout you enter the used pin, in this case 22. Again, click Save and Restart to store the settings on the IoTT Stick, and if selected, in the EEPROM as well. As before, you can verify your settings. You can connect to the IoTT Stick either using JMRI and Loconet over TCP, or a ViceThrottle app like Engine Driver via ViceThrottle Server. Simply activate the server you want to use in the IoTT Stick setup, connect to it and set the turnouts as you wish. I use an LED to verify the voltage change on pin 22 when turnout 2 is changing position. And since I do not have a switch decoder installed, I use a DCC interface and a second IoTT Stick to verify that the DCC command is sent to the track. When doing this, you will notice that there is an offset of 1 between the addresses on the IoTT Stick and the addresses used in DCCX and JMRI as well. The same is the case for sensor addresses, so our sensor 101 will show as input 102 in JMRI. The reason is that the IoTT Stick is using the technical addresses, which start with 0, while JMRI and DCCX are using a counting system starting with 1, even though the technical address behind is 0. I realize this might be somewhat confusing, so I am thinking about changing the way the IoTT Stick addresses turnouts and sensors in a future version of the IoTT Stick software. Now comes the fun part, setting up the LEDs. Open the LED Chain Setup tab. In the General Settings section, I first need to define a long enough LED chain. In my case, with the 8x8 LED matrix, I set this value to 65 to include the onboard LED on the DCC AUX Shield. Then I scroll down to the LED Settings section. By default, the first entry defines the Power Status LED on the DCC AUX Shield. You can change that if you want, but it is not recommended. The first LED on the matrix is LED 1, and here is the table of what I would like to set up. Turnout 1 uses LEDs 2 and 3, and Turnout 2 LEDs 6 and 7. I make them display red or green depending on the turnout position. Then I put the 4 sensor inputs on LEDs 33, 35, 38 and 40, which on the matrix gives a centered arrangement of the 4 LEDs in row 5. As before, I use the dialog screen to enter these settings, click Save and Restart, and when the stick starts up again, the LEDs on the panel should come on and we are ready to test the functionality. As before, I pull down the input pins to ground, and this time I should see one of the occupancy LEDs changing from yellow to red. And when I send a switch command to turnouts 2 or 3, remember the offset of 1, the color of the turnout LEDs should change as well. So I can activate the turnouts, read back sensor information and display the current status on the LED matrix. The only thing that's still missing is the local button input. The buttons work as we have seen in the LocoNet viewer, but nothing happens. What we need to do is binding the incoming events to outgoing activity. To do that, we activate the event handler in the IoTT Stick setup and then open the event handler setup tab. The first event I create is for button 151. The button down event fires when the input is released as it is set to negative. If that happens, a switch command is sent to toggle turnout 1. The next 2 events are for buttons 152 and 153. Both buttons trigger an action to set turnout 2. Button 152 sets it to thrown and button 153 to the closed position. Event 4 finally is to trigger a route. On button down, I send out a list of 2 turnout commands, setting both turnouts to the closed position. The commands are sent out with a configurable delay of 250 milliseconds between them. I then set up an identical route, but this time triggered by switch 5 set to thrown. This means I can send a turnout command for turnout 5 thrown either from JMRI or from the WiseThrottle app to trigger the route as well. As before, we click Save and Restart, and we now can use the local input buttons to trigger the specified action. Button 151 toggles switch 1. Button 152 sets switch 2 to thrown, button 153 sets switch 2 to closed, and button 154 triggers the route, thereby setting both switches to closed. If you have the engine driver app open, you will see the switch positions updated as position commands are sent. And if we check the JMRI LocoNet viewer, we see the messages flowing as well. By the way, you may have to restart JMRI to see the messages, as JMRI does not automatically reconnect to the LocoNet over TCP server once the connection is lost, which happens when the IoTT stick is restarting after saving the configuration. That's a little bit a flaw in JMRI and hopefully will be improved in the future. Engine driver is much more tolerant in that respect and automatically reconnects once the server is available again. Looking over my original requirements, I noticed that I forgot something, and that is an LED indicator showing that the route is set. So I go back to the LED setup screen and define a pair of LEDs that show yellow if both turnouts are in closed position and remain dark otherwise. I pick LEDs 12 and 13 for that purpose, as they are sitting in the second row between the 2 turnouts. And after another save and restart, it works as expected. As soon as both turnouts are in closed position, the 2 extra LEDs turn on yellow to indicate that the route is set. And yes, this is just a very simple example and much more can be done. If you want to see examples of how to set up routes including signals and automatic route release after the train passed, watch the Yellowhead video series starting with video number 69. And that's it for this technical setup. It is now quite easy to print a fascia paper, and there you go. A simple and easy to implement CTC panel display for your command station. It's really not hard to do, and it makes for a nice eye catcher. I hope this information was useful or at least interesting for you, and you are eager to try it for yourself. In the next video I will do a quick introduction of X-Rail and then show how it can be used to implement the IFTTT automation functions right on the Arduino. Subscribe to the IoTT channel and hit the bell icon if you do not want to miss out on that. Also, if you like this video and what I'm showing here, please click the like button below to let me know. Doing so keeps me motivated and helps to promote these ideas and the IoTT channel in general to other model railroaders. Thanks for watching and see you in the next video.